So if we're of course studying multivariate functions, we will of course, our main target is to get to multivariate calculus. And we're now at the point where we want to start looking at how do we differentiate multivariable functions. So for instance, when a function f of x, y, what is the derivative of such a function? Well, the first question is, whenever we differentiate something, we're actually studying the change of that subject of that function with respect to an independent variable. Now, when you have two independent variables, clearly that gives rise to the fact that when you ask a question like what is the derivative, the first question is derivative with respect to which variable. So let's look at some notation. First of all, we use this opposite looking 6, which is delta. So partial f by partial x. This means that we're looking at the derivative of f with respect to x. Now its definition is from first principles. It's the same as before, only now it's more like change in x, delta x goes to 0, f of x plus delta x comma y minus f of x y all divided by delta x. So this represents basically the change in x. As you can see, y remains the same, so we consider y basically steady or constant. So the only change we're looking at is in terms of x. So therefore the derivative is only in terms of x. So a quick example, in a similar way, if we can look at the derivative of f with respect to y, and that would be some change in y where x stays constant. So you would end up with some change in y, and therefore the change in the function, and take away the original function f of x y divided by delta y, and that gives rise to the other derivative, which is y. And in this way you can look at, for instance, if f is a function of x, y, and z, or x1, x2, x3 up to xn, we can look at different derivatives. So the next point is, how do we actually calculate these things? Best thing is to look at an example. So let's look at a quick example. For instance, if we have function f of x y equals x squared plus y squared. Now, when I calculate the derivative of f with respect to x, it means y is considered constant. So the derivative of x squared is 2x, but the derivative of y squared is 0, because there's no change in y with respect to x. Besides, you can see here that in this one that the change is only in x, so y is not changing, so it remains constant in fact. So therefore here, when we differentiate with respect to x, this is just like any number or a constant, so we treat it like a constant. And the derivative of a constant is of course 0, so it's just equal to 2x. Now in a similar way, if we calculate the y derivative of f, that's 2y. Okay, so the derivative of x squared is 0. Okay, so let's look at something slightly more interesting. So here another example. Okay, let's start mixing these up a little bit. So for instance, f of xy equals x squared y squared. Okay, if you look at this, then so if we look at this, partial f by x is equal to 2xy squared, and partial f by y is equal to 2x squared y. So another one, let's look at another example, a bit more complex this time. It's more complicated, I mean. So if we have f of xy equals, for instance, sine of xy, then partial f by x is, of course, cosine of xy, as one would expect. And when we go inside and differentiate the xy with respect to x, that will generate this y over here. In a similar way, if we were to calculate the y derivative, it will still be cosine of xy. That would still remain the same. Only outside we'll have an x this time when we differentiate the inside, which is xy. The chain rule. So you can see the rules of differentiation basically remain the same. It's just that how we use those rules is now quite different. Another example, let's look at this time function x, y, and z, and let's say we have xy log z, an example we looked at earlier. Now I want to here introduce also a notation, which is there is another notation, a shorter way to represent the x derivative, and that is f sub x, and the y derivative is f sub y, which means it's the x derivative, this is the y derivative. And similarly, f z is f sub z. So this is just another notation. So here if I want to calculate fx, which is the x derivative of f, that's going to be y ln z. If I look at the y derivative, it's going to be x ln z. And if I look at the z derivative, it's going to be xy over z. Okay, so a few examples for you to get grips around how the partial differentiation works. Now, suppose we want to actually differentiate this. So I'm sure you might remember the concept of implicit differentiation. Well, there is a similar idea for multivariate functions. So when we want to partially differentiate something like this function here, and if we want to find, for instance, partial z by x, for the sake of argument, this would mean that we're basically taking the x derivative of yz. Now, we are assuming here, we need to know what are the two independent variables. So here we are assuming that z is a function of xy. Okay, so z is a function of xy, but x and y are not functions of each other. So therefore, when we differentiate yz, so basically it would mean we would have y and then partial zx, because y would be considered a constant. The derivative of y with respect to x is 0, in fact. Here you'd have 1 over z multiplied by partial z by x, and on the other side you'll have the x derivative of this is 1, and the x derivative of y is 0, as seen before as well. So now you simply rearrange the equation, so partial z by x, take it out common, so you got 1 minus 1 over z, and that's equal to 1. So therefore partial z by x is equal to, basically this is zy minus 1 over z, so it'll be z over yz minus 1. Okay, so just to clarify, what I did here is, if you look at this one here, y minus 1 over z is just z yz minus 1. Okay, so I just turn that upside down as it goes to the other side. So that's my x derivative. So here's an example of how implicit differentiation and partial differentiation works. Implicit partial differentiation.